Hi, I'm Lexie. I'm working under the supervision of Doctors Alasdair, Syme, and Ian Hill, and this is my summer work on Monte Carlo simulations of the response of an organic electronic device to ionizing radiation. In our group, we work with dosimeters, which are devices that measure the dose deposited from ionizing radiation. If a dosimeter were placed on the body, we want these devices to be able to read the dose that is being deposited in tissue in that region of the body. This is the device we've been looking at, and it's composed of mostly organic materials, which tend to be more tissue equivalent. We've tried using two different source and drain electrode materials, gold and PDOT-PSS, which is an organic conducting polymer. The organic semiconductor is pentacene, and there's polystyrene and silicon dioxide as dielectrics. Our gate is silicon. This is some preliminary data of the device responding to dose. We can see how the current at the drain is shifting with increasing dose, so we know the device works. To see how the dose is being deposited in different layers of our device, we can use Monte Carlo simulations, which is a stochastic model that predicts the outcomes of particle transport by using probability distributions, going particle by particle. These are the results from the Monte Carlo simulations. This graph is the dose deposited in the pentacene and polystyrene layers of the device, relative to the dose deposited if the device was replaced with water, as water is tissue equivalent. Here you can see the device with both the gold and PDOT-PSS electrodes. The ratio is constant at around 1 for higher energies. This is because the Compton scattering is the dominant effect for high energy, and it's independent of atomic number. Ideally, we want this ratio to be constant over all energies, but at low energies, the photoelectric effect is dominant, and it is dependent on atomic number. So here at low energy, the gold electrodes is causing a very large perturbation in the dose deposited in the pentacene and polystyrene layer. But by just switching the electrodes to an organic material, the ratio is reduced significantly. We also did simulations replacing the top 3 layers of our device with water to see how just the silicon and silicon dioxide are affecting the dose in the other layers. You can see here the dose is very similar to that of the whole device with PDOT-PSS. This leads us to conclude the perturbations left is mainly from the silicon and silicon dioxide layers. If we were to replace these layers with an organic substrate and conductive organics, we'd expect the dose in the low energy region to be significantly reduced and to be more constant over all energies.